Imagine a brilliant sculptor carves a statue. It's perfect, detailed, a masterpiece. But it's frozen in time. What if, instead, they could create a river? Something that has a form, but is constantly flowing, changing, and adapting to the landscape around it. What if our AI could be more like that river?
That's a beautiful way to frame it, Maya. Because for a long time, our AI models have been statues. We train them, we perfect them, and then we deploy them in a fixed state. But a new approach, called liquid neural networks, is trying to build that river.
Okay. Liquid neural networks, or LLNs. It sounds incredibly futuristic. So let's start with the problem they're trying to solve. Why is a frozen AI not always what we want?
Because the real world isn't static. It's constantly changing. A self-driving car encounters roadwork that wasn't in its training data. A medical sensor sees a pattern in a patient's heartbeat that is entirely new. A traditional, frozen model struggles with this. It's brittle. It only knows what it's already seen.
Right. It can't learn on the job.
Exactly. It can't update its understanding of the world without being taken offline, completely retrained on a massive new dataset, and redeployed. That process is slow, expensive, and requires a ton of data and computing power.
So, enter the river. How does a liquid neural network avoid being frozen?
It goes back to the fundamental architecture. Most neural networks you hear about, like the ones in GPT or Midjourney, are built in discrete layers. Data goes in one side, passes through layers of digital neurons with fixed mathematical weights, and an answer comes out the other side.
A very complicated but rigid assembly line.
A perfect analogy. LLNs are different. They are continuous time systems. Instead of rigid layers, they are modeled by a system of differential equations. Think of it less like an assembly line and more like a small dynamic ecosystem of interacting parts.
Differential equations. That sounds like physics or biology. Is that where the inspiration comes from?
It is. A key source of inspiration, cited by the researchers at MIT like Ramin Hassani, who pioneered this work, is the nervous system of a tiny nematode worm, C. elegans.
A worm?
Yes, this worm has only 302 neurons, not millions or billions, just 302. Yet it can find food, avoid predators, and navigate a complex world. Its nervous system isn't a static computer. It's a dynamic, wet system. The LLN architecture tries to capture that principle, creating rich, complex behavior from a very small, efficient, and adaptive system.
Okay, that's a powerful idea, but I'm still trying to grasp the liquid part. If the system is defined by equations, where does the ability to change, to flow, come from?
This is the core innovation. In a standard recurrent neural network, or RNN, the connections between neurons have weights that are fixed after training. In an LLN, the underlying parameters of the differential equations that define the network's behavior are not static. They can change in response to the incoming stream of data.
So the network is actively rewriting its own rules as it experiences the world?
That's a very intuitive way to put it. The state of the network isn't just the output of the last calculation, it's the entire dynamic system. When new data comes in, it doesn't just produce a new answer, it can subtly alter the system's dynamics. This allows it to adapt its behavior over time, making it a model built for what's called continual learning.
And this connects back to the worm with its 302 neurons. The claim is that LNNs are also highly efficient, right?
Incredibly so. This is perhaps their most practical and immediate advantage. Because the architecture is so dynamic, you need far fewer neurons to accomplish complex tasks. We're talking about models with maybe just a few dozen neurons, not thousands or millions.
Wait, dozens? That seems impossibly small.
It is, compared to what we're used to, but it's a different kind of computation. It's not about having a massive web to find a static pattern. It's about creating a small, responsive system that can model the dynamics of a time series of data. This sparsity, this small size, means they require a tiny fraction of the computational power of conventional networks.
And if they're that small and efficient, it means they don't need a massive data center to run. They can run anywhere?
Exactly. This is the promise of Edge AI, or on-device AI. You can run a sophisticated adaptive AI model directly on a tiny chip inside a drone, a car, a smartwatch, or an industrial sensor. Think about an autonomous drone navigating a forest. An LNN-based flight controller can adapt in real time to sudden wind gusts or unexpected obstacles, learning and adjusting continuously.
So the data doesn't have to be sent to the cloud for processing. That has huge implications for speed and privacy.
Massive. The latency is practically zero, which is critical for a car that needs to brake or a drone that needs to swerve. And for privacy, if the data from your personal medical device is processed on the device itself, it never has to leave. It's a much more secure and private way to build personal AI.
Let's get more concrete with applications. We've said cars and drones. What else?
Time series forecasting is a major one. LNNs are exceptionally good at processing data that arrives at irregular intervals, which is common in the real world. For example, predicting the remaining useful life of a jet engine component based on sensor readings. Those readings might not come in perfectly spaced intervals, and the patterns indicating failure might evolve over time.
The LNN could adapt to those evolving patterns?
Precisely. Another area is human-computer interaction. Imagine an interface that adapts to the unique way of gesturing or speaking, continuously refining its understanding of you. Or in healthcare, a wearable that doesn't just look for known bad signals, but learns your personal baseline of what's normal and alerts you to subtle, slow-moving deviations over weeks or months.
That's a profound shift. It's moving from a one-size-fits-all model to a personalized one. But it raises a question for me. If the model is constantly changing, how do we trust it? Doesn't it become even a black box?
That's one of the most fascinating aspects. Counterintuitively, they can be more interpretable. Because the models are so small, and because they are explicitly modeling cause and effect through differential equations, we can actually probe the system. We can look at the hidden state of the network over time and see how its internal dynamics are responding to the input.
You can watch it think in a way.
You can watch its dynamics unfold. The researchers have shown that the network's output is often a smooth, causal function of the input. It's not just a black box correlation, it's modeling the underlying system. This allows for a degree of transparency that is very difficult to achieve in a billion-parameter static model.
So it's smaller, more efficient, more adaptive, and potentially more trustworthy. It sounds like the future. Why isn't this everywhere yet?
It's still a relatively new field of research. Training these models presents unique mathematical challenges, though the field is advancing incredibly quickly. We're seeing them move from academic papers into real-world tests now. But it represents a significant paradigm shift from how the industry has built AI for the last decade. Change takes time.
So we're shifting from building AI like static architecture to cultivating it more like a garden or guiding it like a river. It's less about achieving a final perfect state and more about enabling a process of continuous becoming.
That's it. It's a move from static intelligence to dynamic, adaptive intelligence. And that feels much closer to how biology and life itself actually works.
So if there's one thing our listeners should take away from this conversation about liquid neural networks, what would it be?
The key takeaway is that LNNs offer a path towards AI that learns continuously from its environment. By using dynamic systems inspired by neuroscience, they are incredibly efficient and robust, paving the way for powerful AI to run on small, everyday devices, from your watch to your car.
It's AI that doesn't just know, it adapts. Thank you for listening to The Clue Matrix.